evening. Oh. Look at that. It's been quite a long day. Thank you all for coming. Thank you for making it on this lovely evening. I suppose one of the things I want to say this evening is that physics is hard. Or maybe we could be more specific, I suppose. Cosmology, the study of the universe as a whole, is hard. But it's not hard, I think, for the reasons that lots of you think it might be. It's not hard because studying the universe as a whole is inherently complex. The universe is simple. I mean, especially once you decide you don't care about details like all the stuff that happens down here, how you form planets, stars, galaxies, life, biology, chemistry, all of that. Let's ignore all of that. If we just write down the equations that explain the past, present, and future of the universe, they're simple. You can fit them on a couple of pages of A4 paper. And it's much easier to predict the fate of the universe than it is to tell you which way a cricket ball will spin as it leaves a bowler's hand. This is true. It's also not hard because we're short of ideas about how the universe might behave. We're not short of theories, of speculations, of crazy ideas about what might be the fundamental reasons for the universe behaving the way it does. Lots of us get emails all the time from people who've had a bright idea about how the universe works. And these emails I like getting them. It's nice to know people are thinking about these things. But there's a sort of impression that the person writing often has done the hard work of having the idea, and could we fill in the details? Like we've all been sitting around in what one of my colleagues calls the Hollywood version of science, where we all sit around until somebody has an idea and goes, my God, I've got it, and then we all run off and prove them right. It doesn't work like that. We've got lots of ideas. The hard bit is getting an idea that matches the vast amount of information that we have about the universe, that your bright idea about why the universe is expanding, or how much matter there is, or how atoms behave. Can you get your bright idea to not break what we already know about the universe? That's the hard bit, because we've got more than a century of cosmological observations which we believe in. And most of them, the single observation that constrains our ideas most, comes from what I've been calling the oldest light in the universe, the cosmic microwave background. And that's what I'm going to talk about this evening, if I can get up onto the stage. Now, when I talk about observations in the universe, there's a fundamental fact that I've mentioned several times in these lectures, which is that light travels at a finite speed. So what we see of the universe is not the universe as it is now, but we see objects as they were when the light left them. So the unsettling version of this is that light travels at about a foot per nanosecond. So if you look down and see your feet, if you're sitting, you're seeing your feet as they were 3, say, billionths of a second ago, not as they are now. I don't really know what to do with that feeling. It's kind of unsettling. I suggest trying to forget it. We'll go to larger scales. We see the sun as it was 8 minutes ago. And so if I get rid of the sun by clicking my fingers, that doesn't work, I hope. But you can't prove that I haven't done it for another 8 minutes, because its light will still be streaming towards us. And actually we know, for reasons I can talk about in the questions, gravity travels at the speed of light as well. And so the sun's gravitational influence we experience as it was based on where the sun was 8 minutes ago. We look further into the night sky. You can take your pick of the naked eye stars. Let's do Deneb in the constellation of Cygnus, the Northern Cross or Swan, which is particularly prominent in the northern hemisphere at the minute. Deneb's actually one of the more luminous of the naked eye stars, so we see it as it was about 2,500 years ago. So we're looking back into the past. Again, if Deneb had disappeared in the last 2,500 years, we wouldn't see it. And, of course, anyone on a planet around Deneb will see us as we were a couple of thousand years ago. We can go further. We can look at the furthest object that's easily visible with the naked eye, the Andromeda galaxy. Here it is, M31. In the autumn, if you're lucky and you're in a dark sky, you know where you're looking, and you've got clear skies, and your vision's pretty good, you can just about see a smudge of light that is the Andromeda galaxy. And those photons, those particles of light which are reaching you from Andromeda, have been traveling for 2.2 million years. Some of you in the audience, perhaps the younger members of the audience, you could just about see Triangulum, the next big galaxy out. That's 2.7 million light years away. So we're going into the past. The cluster, for example, this is an image that was released just this week by the European Euclid telescope, something that's designed to make observations that help with this problem of understanding the universe on the largest scale. Mostly, it's a beautiful picture, but it's also showing us a cluster called Abell 2390, which is 2.7 billion light years away. And so we're now at the point, when you get this far into the universe, the idea of a present of today's universe has sort of vanished. We're seeing in these images a deep past. Galaxies are different processes are happening, the universe is a different place, but we get to observe it. And of course, we can go even deeper. This is a recent image from the JWST, our newest space telescope, and many of these dots are interesting. Many of these dots are galaxies, not nearby stars, but one of them down here in the bottom corner, which delights in the name GNZ11. Sorry, it's American, GNZ11. I've been told I've got to translate that. This is a galaxy, this little dot. I know it doesn't look like much, but this is a galaxy seen 430 million years after the Big Bang, so more than 13 billion years ago. I mean, we're looking at one of the earliest active galaxies that have ever been seen in this image. So we really get to write down the long past, the long history of the universe. Now, I said this image was from JWST, and I don't have an image of it in action because it sits more than 1 million miles away from us on Earth, but here it is just before launch. It's gold mirrors folded away, and what it's sitting on there, that structure, which is about the size of a lawn tennis court, is a sun shield. So it's designed, when in flight, to always protect the mirrors and the instruments of the telescope from the light of the sun. There's quite a fun fact, which is that you can measure its effectiveness in the same units that you do sunscreen. And so that sun shield, which cost many millions of dollars, has an SPF factor of 1 million, just as designed. It's quite nice that you can use these familiar units. And the reason you go to all that trouble, the reason that you have to keep JWST cold, is that it's an infrared telescope. It doesn't work in the light that we can see, but it works at light at longer wavelengths in the infrared. And it has to be an infrared telescope in order to see galaxies like this one, because they shine most brightly. When you get to the distant universe, the galaxies shine most brightly, not in visible light, but in the infrared. And this should seem like a puzzle, I think, to you, because when we say that galaxies are shining, mostly what we mean is that the stars in them are shining. When we see this galaxy as it was more than 13 billion years ago, what we're seeing is starlight from more than 13 billion years ago. And stars, locally, in the galaxies that surround us and in our own Milky Way, stars like Deneb, shine most brightly in the visible region of the spectrum. Indeed, that's probably why it's the visible region, right? We evolved to make use of the light from the sun. It makes sense that we see in regions of the spectrum where the sun is bright. But these galaxies, which still have stars, shine most brightly in the infrared. And it turns out that's not because the stars are different, but because the light from them has been affected by its passage through the universe. We say it's been redshifted. It's been moved to the red. And we can measure this redshift very precisely by looking at the spectra of stars. So here's an image I've shown before, I think. This is the spectrum of the sun, with the light split out so that it forms the whole rainbow, and we've wrapped it round on this picture. But you can see that in this spectrum there are these dark lines, these fingerprints that tell us about the presence of different atoms in this, in the stars, in the sun's atmosphere. So the two broad black bands that you see in the yellow there tell us that the sun has sodium in its atmosphere, for example. And when we look at distant galaxies, we see the same pattern of fingerprints, but all shifted to the red. And we call that the redshift. And so it tells us that something has happened to the light from these distant galaxies while it's been on its way to us. We think the stars are normal, but this redshift has happened. And we've been studying this sort of thing for a long while, for more than 100 years now. And a slightly unsung hero of this story is this guy. This is Vesto Slipher, pictured as a relatively young astronomer. I think it has to be said, I was determined, at one point this lecture was going to be about Vesto Slipher, because I think his work is incredible, as you'll see. But he turns out to be incredibly boring. I mean, I'm sure he was lovely, I'm sure he had hobbies and stuff, but the historical record records that he grew up in a scientific family, went to college, liked astronomy because he had a good professor. His brother, who was an astronomer, got him a job at an observatory, and then he stayed there for 53 years. So, you know, I can't really make much of a lecture of that, but what I can tell you about is his results. So he was working at Lowell Observatory, the place where Percival Lowell had set his astronomers to look for canals on Mars a few years earlier, where Pluto, actually under the supervision of Slipher, was discovered in 1930. Though, of course, that's turned out not to be a planet, and we can fight about that again in the questions, if you like. But he was interested not in solar system astronomy, but in studying the broader universe. And he got engaged in the problem of what was called then the problem of the nebulae, the fuzzy things that you see in the sky, the things that aren't stars. And it was known in the early 20th century, as I've covered in previous lectures, that some of them were spiral nebulae. They had a spiral structure, and those appeared to be different from things like the Orion Nebula, which we now know to be star-forming regions. Slipher used the powerful telescopes at Lowell to take spectra of these spiral nebulae, and he noticed that within them, the lines, those fingerprints that I showed on the previous slide, were shifted back and forth. Some of them were shifted to the blue. Some galaxies, some spiral nebulae, showed lines shifted to the blue, and some showed them shifted to the red. Over time, and by 1917, when he wrote this paper, it was clear that there were more red than blue. He, at the time, in this paper, he reports a ratio of 21 redshifted galaxies to 4 blue-shifted. So he sees this imbalance in the universe, and he interprets this shift as motion, that these galaxies are moving relative to us. He does that because you can make an analogy between this kind of shift and a Doppler shift, the kind of thing that causes an ambulance siren to change pitch as it flashes past you. It's not quite the right analogy, it's not quite the right physics as it turns out, but it's a good thing to bear in mind that you can convert these things to velocity. Now he's excited by this because to him this tells us that we live in a galaxy. The fact that all these galaxies are moving relative to us, but our nearby stars are not, tells him that we live in a galaxy. So he is most engaged in the fact that he's shown that the Milky Way is something like those distant objects. And he says that we can work out how the Milky Way is moving. He says it's moving at 700 kilometers per second, a number that I'll come back to. But his results are used by a much more famous astronomer. They're picked up by a man with a pipe around town, Edwin Hubble, down the road in California, who was studying the same sets of galaxies. Now, Hubble was more interesting. I've always been a big Hubble fan, partly because he's one of the, unlike Slipher, who seems to have been born to this, Hubble definitely fought for and chose to be an astronomer. He originally, under parental pressure, became a lawyer and was given the best training, I think, at the University of Chicago. And then he was a Rhodes Scholar in Oxford, where I've looked and looked and looked, and we have no record of him taking any interest in astronomy whatsoever. I thought I'd find the lectures that converted Hubble from law to astronomy. But he was doing all of this as law, which he then went on to practice half-heartedly, he said, before chucking it for astronomy. And there's this great quote, he says, "Even if I knew I was second or third rate, it was astronomy that mattered." And I could, I suppose, work most of a lecture around that. I found some nice colour. I've actually known for a while. So the great fact about Hubble is that he was on a championship basketball team when he was at college. And you're thinking, why am I telling you that? I'm telling you that because the basketball has been to space. So this is the basketball on the Space Shuttle Atlantis while it was visiting the Hubble Space Telescope, which you can see just popping out the top of the picture there. So that's pretty good bragging rights, I think. I've held the basketball that went to space that Edwin Hubble once played with. So, I'm practically as famous as him, I think. I'm also terrible at basketball, it turns out. What Hubble was doing was slightly different. So Slipher had looked at the spectra, but Hubble was taking deep pictures of the galaxies around us using the large telescopes at Mount Wilson in California. So that on the left is a modern picture of the Andromeda galaxy, but on the right here is Hubble's picture from 1923 using the great 100-inch telescope. So what's that? That's about 2.5 meters, the mirror across. And you can see he's marked a couple of N points on here. There's one in the middle, there's one a bit further up. Those he thinks are novae. They're exploding stars. They've appeared since his previous observation. And there's one in the top right where he's labeled it N, and then he's crossed it out and written VAR, which is not a sporting reference. This is the discovery of a variable star, a star that's changing in brightness over time. It appears and disappears as he takes images of this galaxy from night to night. And in fact, it's a type of variable called a Cepheid. Now, a Cepheid variable, and this is the pattern of that star, these are modern observations of Hubble's variable star. You can see it goes up and down in brightness with this regular pattern. And the crucial thing is that the speed with which it does that tells you how bright it is, or rather how luminous it is, how much power it's putting out in its light. And so if you know how luminous something is, and you know how distant, and you know how bright it appears in the sky, you can work out a distance to it. So Hubble has this method which builds on great work by Henrietta Leavitt and others, particularly the women of Harvard Observatory in the first couple of decades of the 20th century. But Hubble's able to make these observations because he's got access to these big telescopes. And so he's able to measure the distance to the galaxies that Slipher is taking spectra of. And the results are quite striking. These are Hubble's results. I've replotted them. But I've put nearby galaxies on the left and distant galaxies on the right. And on the y-axis, so at the top here, that's the amount of redshift. So the higher up you are, the more redshift there is. You can interpret that as a velocity if you want. And so what you can see is that there's a rule here that we now call the Hubble-Lemaitre law. And the rule is that the further away a galaxy is, the faster it's moving away from us, the greater the redshift. The further away a galaxy is, the faster it's moving. Here's the modern version done with the Hubble Space Telescope, and you can see that the results are really quite convincing. And that observation is, I think, the most important ever made in the subject of astronomy. Because from that, we get all of modern cosmology. And to show you why that is, I think we need a slightly different universe to think about. And I like using this. This is an Escher print called Cubic Space Division. And I want you to imagine that we live on this cube that's at the bottom. So we're just here, all clustered on this cube. And I want you to imagine that in this universe that Escher's visualized and that I'm talking about, the rods that join the cubes together are all expanding. And they're all expanding at the same rate. And it doesn't matter what that rate is. Let's say it's, 10 miles an hour will do, something like that. So the first thing you realize is that if we're on our cube at the bottom and all the rods are expanding, it's going to look like all the other cubes are rushing away from us. We're going to feel like we're in the center of some great expansion. But that would be true whichever cube we lived on. So there's nothing special about the fact that we look like we're at the center here. Second, this cube, so if we're here, this cube here is going to rush away from us at 10 miles an hour. But this one in the top right is going to go away at 20 miles an hour because there are two rods between us and it, and each one's expanding at 10 miles an hour. So there's a rule in this universe that the further away a cube is, the faster it's receding from us. The further away the cube is, the faster it's receding from us. That's the same rule that we found with Hubble's observations. And so replace the cubes with galaxies, ignore the expanding rods and say it's space itself that's expanding, and you get Hubble's law back at the cost of admitting that we live in an expanding universe. And that's the fundamental insight that leads us to what we'd call the Big Bang theory. Because if you live in this universe where things are expanding, we can run this backwards, and you get to a point where all the cubes are next to each other. A dense universe that then exists just after the start of a universal expansion. So that's the moment just after whatever the Big Bang was. And so that's the observational evidence. There are other lines that support it. That's the observational evidence that supports this crazy idea of a Big Bang. And I should say in passing that it is a crazy idea, right? The idea that the universe had this moment where things came into being, perhaps, and then there was this expansion. That's not simple physics at all. That's not obvious that it should be so. And in fact, the name Big Bang came from somebody who believed that the idea was ludicrous. It was given by the great Cambridge cosmologist Fred Hoyle, the man who, with others, explained how stars produce heavy elements. He thought this idea was ridiculous, and Big Bang was used by him for the first time in a radio address as an insult. You know, this Big Bang theory can't make any sense. That's what it was supposed to be. There have, by the way, been attempts to remove the name because it's slightly, I don't know, it's slightly confusing, right? We're not saying there was an explosion, we're just saying there was a time when all the cubes were on top of each other and the universe was in this dense state. Sky and Telescope magazine in the 90s ran a competition to replace Big Bang. They asked for suggestions. And there was a strong second place showing for horrendous space kablooey, which some of you may recognize from Calvin and Hobbes, but it's a bit of a mouthful, and Big Bang won the contest. So we're stuck with it. But it raises questions. It raises questions like, what caused the Big Bang? We've got this moment, which seems to be a moment of origin. So what caused it? And this was a question that was immediately obvious to those who were working on theory alongside Hubble and so on. And there was a nice idea that maybe you had a cyclical universe. So the universe would expand, perhaps it would slow down, it would reverse, it would contract, and it would come back to whatever the opposite of a Big Bang is. Tends these days to be called the Big Crunch, but there was a brief period where it was a Big Bang backwards, so it's the gnab-gnib, which I think is about right. If you're watching at home, you can play that backwards and see if I got that vaguely right. And that's really nice, because then you just have a universe that bounces along forever. You never need to explain what happens. Except that it was obvious, even by the 50s, that there's a problem with this idea. And the problem is that the universe changes its contents. So let's go back to that distant JWST image and this blob of a galaxy that I am going to keep showing you until you're excited by it, even though it's a small red dot. One of the things that's exciting about this is that we've detected gas around it. And the gas is almost entirely hydrogen, we think, but definitely helium and not much else. And so in our modern cosmology, this makes sense. The early Big Bang, the conditions that existed right at that moment where things were very dense, we think produced hydrogen and helium. And so the fact that this galaxy, which is only a few 100 million years after the Big Bang, has this pristine gas around it, that suggests that it's young. That makes sense. That's what we'd expect for a galaxy that's in the first flush of youth. But what bothered people in the 50s is that over time, as this universe evolves from here to us today and onwards, stars turn hydrogen and helium into heavier elements, into the carbon, oxygen, nitrogen, everything else that we're made of, into iron, and explosions produce gold and so on. The universe becomes polluted with these heavy metals. And so if you have this cyclical universe from Big Bang to nab-nib, definitely the first one was better, nab-nib, then shouldn't you inherit some of the leftovers of the previous universe? You need a magical process that destroys everything and gets it back to pristine hydrogen to explain what we're seeing. And so they started to look for evidence of such a process. And that's the next bit of the story. But it starts in a very different place. It starts with an extremely large balloon. This is a balloon called Echo 1. This is its first inflated test. And this is, I think, the simplest working satellite ever launched into space. It was just a big balloon. It got to space, got to the very upper atmosphere of the Earth. It's a NASA project. And the idea of Echo 1, and there was an Echo 2 and a couple of others as well, is that these, launched in the early 60s, were passive communication satellites. So in other words, you put these big shiny balloons up in the upper atmosphere, and then if you want to communicate with somebody who's over the horizon via radio, you can bounce your radio signals off the balloon. It's really simple, but it works, right? And it's important. So this was an attempt to improve radio communications, but which triggered a huge interest in trying to understand the kind of background interference that you got when you did this sort of communication. No doubt, even if you had a powerful radio transmitter, bouncing it off a shiny balloon in the upper atmosphere means that the signal coming back down to your target station is going to be really weak. And this is even more true when things got a bit more advanced. When we had the first communication satellites, this is a model of Telstar, which was the first privately built and supported satellite. Telstar was a relay, so you could beam television signals up to it, and then it would beam them back down to Earth, but it was going to be faint. And people built big instruments like this AT&T ground station in Maine that were built just to communicate with this one satellite so that we could communicate across the globe. But understanding the background, as so often in radio astronomy in particular, but in astronomy as a whole, had become really important. And that brings us to this instrument. This is the Big Ear, which exists in Homedale in New Jersey. It's still there. It looks rather like it did in this picture. It's just been announced that it's going to be preserved as a historical monument, which is great, because when I went to see it, I had to break through a fence in a Nokia car park to go and see it. But standing on here are two gentlemen called Penzias and Wilson. They were engineers at Bell Labs who were given the task of characterizing the background that was interfering with transmissions to things like Telstar. You can see that they have their giant antenna. There's the shed on the end is where the electronics live, so that's where the receiver is. So this collects radio waves, focuses them down into the shed, and crucially the whole thing rotates so that they can swing it around the sky and try and work out what the source of the background is. Now this thing is a museum piece. We couldn't build one of these just for demonstration purposes. I did ask, but apparently Conway Hall isn't quite big enough. So I've bought my own device that's operating at the same wavelengths. Now, some of you may recognize the rough form of this thing. Some of you may not, but this is what they used to look like. So this has an antenna, and it's tuned to a particular frequency, and as you can see, it's receiving static, because analog television transmissions were turned off in this country about 10 years ago. So this is all we can get. But this is operating at the same wavelengths as the Big Ear. And so this is picking up the same static that Penzias and Wilson were trying to attract. So you can actually see it this evening. This is a live demonstration. This isn't recorded. I hope you're enjoying it. I know, perhaps it's more interesting than the lecture. Never mind. They found that most of their signal, 95% of it, was due mostly to atmospheric effects, to distant lightning storms, to things happening in the upper atmosphere, to the radio background that the Earth creates, thanks to its magnetic field and the atmosphere. But they found there was a remnant, about 5% of the signal would not go away, and they spent a long time mapping the sky to see where that 5% was brightest. And I actually replotted it for you, but this is their data plotted on a modern map of the sky. So I've got the whole sky, and this shows you all the variation that they detected. It was completely uniform. So this is coming from wherever they pointed their antenna, they received a signal with the same strength. And if this thing was more stable, I could rotate it and show you that this doesn't change. I discovered earlier that doesn't work very well, so we won't do that. Now, if you have a uniform signal, it's usually a sign that something's wrong with the instrument, right? That there's a cable loose, or the antenna's got its own source of noise, because as you swing it around the sky, nothing changes. It seems clear it'll be noise. My favorite analogy for this is the 19th century astronomer who reported the discovery of giant ant-like forms on the moon. because he could see them through his eyepiece whenever he looked at the moon. And it was only when he realized that he could also see them when he looked at Mars and Venus and several stars that he realized that the ants were local, right? They lived in the eyepiece. The paper was, it's a true story, it's a genuinely true story, and the paper was retracted. And I have checked, I have never seen giant ants on any of those bodies. So we know that was noise, right? That was a mistake. And Penzias and Wilson originally thought that they had a similar problem. Their paper tells us that their antenna was coated with what they called a white dielectric substance, which was deposited there by pigeons that had taken up roost in the antenna. They found a solution. This might be my favorite slide of all year. This is the actual pigeon trap they built to catch the pigeons. This is currently in the collections of the Smithsonian Museum. So if you're ever in Washington, D.C., you can go and ask to see this pigeon trap, which I highly recommend. Weirdly, the electronics from the antenna are in Berlin, but D.C. got the pigeon trap. Somewhere there's a museum story about that. They caught the pigeons. Let's assume that they took them a long way away and released them safely. I haven't been able to find any records. They came back, and then they scrubbed the antenna with toothbrushes. So I want you to imagine being a highly trained engineer who solved 95% of the problem that you were set, getting rid of this noise in the background, and there's 5% left. And I want you to imagine that that's led you to catch some pigeons and then scrub your antenna clean of what they've left behind. He says, suddenly realizing, I don't know if I can swear at Gresham, but never mind. You understand the role of the pigeons. Scrubbed with toothbrushes. And then I want you to imagine you go back into your cabin, you turn on your electronics again, and you find that hum, that background noise is still there. And I want you somehow to imagine that you're excited by that. And that you don't just write in the report, there is a background hum which remains anomalous. Done. Instead, they started seeking explanations. And in seeking explanations, they were put in touch with a group of cosmologists just down the road at Princeton who'd been thinking about building an experiment to detect a background hum at exactly these frequencies. Because they realized that that was their solution to the bouncing universe problem. You see, if that dense state that happens just after the Big Bang is also a time in the universe's history where it was very hot, then atoms can be ripped apart by the aftermath of this hot Big Bang. And so even if you start your universe with a complex set of pre-made atoms and maybe even molecules, if you go through a hot Big Bang, then you reduce everything to a sea of particles right at the beginning. In fact, if it's hot enough, you can't even have atoms. You can't even have neutral atoms because the electrons, which normally orbit the protons or the atomic nuclei, will run free in the universe. And so we predict that that early universe should be a sea of electrons. And that has interesting effects. The effect is that light traveling in that early universe won't go more than a fraction of a centimeter before it hits an electron and is scattered in a random direction. So if I click my fingers and send you all back to a time 200,000 years after the Big Bang, which I can't do, but you can imagine, if you're there in the first few 100,000 years after the Big Bang, you'll find yourself inside a luminous fog because light won't be able to travel for more than a centimeter or so in front of your face. And so it will bounce around and bounce around. But we know the universe is expanding. And as it expands, it cools. And there comes a point, about 380,000 years after the Big Bang, where all the electrons can be captured by the nuclei. An event that happens really quickly. It takes about a year for the whole universe to go from a sea of electrons to empty space. And at that point, light which is bouncing around can suddenly travel across the whole universe. So this is a nice example of that. This is an artwork called Blind Light by Anthony Gormley. It's a box of fog with some lights in it, if you'll forgive the description. But the point is, from outside, there's a light bulb in there somewhere. The light bounces around, but it keeps hitting water molecules. And it bounces from water molecule to water molecule to water molecule to water molecule until it happens to hit the edge of the glass. And if it scatters in the right direction, it travels out across the room. And we perceive it as having come from a glowing edge of this box of fog. So when we look back at the early universe, we encounter light that has bounced around from electron, electron to electron to electron, and then suddenly when the electrons have disappeared, it flies across the universe and it's detected by this device, by this television next to me. So 5% of that static on this screen now genuinely comes from a time 380,000 years after the Big Bang. That's what's been getting in the way of trying to watch, I don't know, late night comedy on Channel 4 30 years ago, I suppose, in my case. Anyway, we can actually study this first light, this early light. We call it the cosmic microwave background. And later satellites, because it's best to do this from space and not with televisions, started to find structure in the background. The first thing you see if you have a sensitive instrument, not just the big ear, is that you see there's a dipole. So this is a map of the sky again, and it's slightly hotter and colder. Think of it as brighter and fainter at particular wavelengths. This is because we're moving through space. So this tells us about the Earth's motion, and it turns out we're heading towards something called the Great Attractor, a collection of about 100,000 galaxies, a few 100 million light years away. But we can get rid of this pattern, and then you see this, and this stripe along the middle is actually our galaxy getting in the way. Dust in our galaxy emits at these wavelengths. So you take that away, and then you end up here. And these blobs, which were first seen by a satellite called COBE in results released in 1992, are, I think, the thing that convinced most working cosmologists that our model of the Big Bang was real. And it's because if you have a completely uniform universe, that doesn't look like the universe that we see today. The universe that we see today, and is the map of our local universe that I showed in Lecture 1. This is data from the Sloan Digital Sky Survey. You'll see our universe today is lumpy. There are places where there are lots of galaxies, and there are places where there are very few. But if we have a microwave background, an early universe that's completely uniform, then it will remain uniform. You won't be able to form the lumpy universe that we see today. But once we discovered that there were tiny fluctuations, and they're small, they're about 1 part in 10,000 difference in density or temperature between each of these blobs. Once we discovered there were these differences, we could work out how galaxies form. And we do that using supercomputers like this one, which is artfully framed in an old deconsecrated church in Barcelona. Just looks fantastic. And what we do is we can take the blobs that we see in the cosmic microwave background, we scatter material, matter, in this distribution in the computer. So you get this. And in a picture like this, which is of the computer simulation, the bright bits are the places where there's more matter, and the dark bits are places where there's very little. And this is, 15 million years after the beginning. The differences are pretty subtle. But gravity works to exaggerate those changes over time, because the bits of the universe that already have more matter than the average will accumulate more matter. They have a stronger gravitational pull. And so as time goes on, through 1 billion years, nearly 5 billion years up to today, we go from a very smooth universe to the lumpy one that we see today. I've taken out the expansion in these images so you can see what's going on. And here's a movie showing roughly the same thing, where you can see the structure becomes defined over time. And the game we can now play is that we can compare this to the universe that we see around us. And then because we know the starting conditions from the CMB, we can work out what other ingredients we need in the universe to produce the one that we see. And so this is the fundamental observation that's taught us so much about the universe. Comparing these simulations to things like the Sloan set of data gives us the recipe. So it tells us, for example, that we know that there's 6 or 7 times as much matter in the universe than we can account for in normal matter, in hydrogen, helium, and all the rest, in protons and neutrons and all the rest. We know that that's dark matter. Don't know what it is, but we know that it's there. We also know through comparisons like this that the fate of the universe is settled, that the expansion of the universe is actually speeding up for reasons that we don't understand. We tend to label that dark energy, but we don't know what it is. And so we don't get our gnab nib, we get an ever-expanding universe at the end. And so this is the game that cosmologists play. This is why it's hard, because I have to, when I write down my new idea for a cosmological theory, I have to still produce a universe that looks like what we see. I have to get the cosmic microwave background right, and I have to tie them together. And that's really hard. What we'd like to happen, actually, is for the observations to disagree with each other a bit, because then we'd have a clue as to which ideas might be good ones. And we're beginning to get the idea that that might be possible from 2 sets of observations, trying to measure something fundamental, something that Hubble himself would have recognized. All we want to do is measure the current expansion speed of the universe. How fast is the universe expanding? This is sometimes called the Hubble constant, though it's not constant, it's just the current value. Now, there are broadly two ways of doing this. One is that we can look at the cosmic microwave background, we can do that extrapolation to what we see today, we can compare the two, and we can work out how much expansion there's been. It's a bit like having a cosmic ruler. We can take features in the cosmic microwave background, we can look at our distribution of galaxies and say, okay, we found the same feature, so we've literally measured how much bigger the ruler has got. It's really simple. It's a physicist's way to do it. It's elegant. It's difficult. It's tricky. You've got to get the statistics right, but it's nice and simple. Or you do a better version of what Hubble did. And he measured distances with stars. So now we use exploding stars. This is a type 1a supernova, the death of a giant star in a nearby galaxy, M82. And these always go bang with roughly the same brightness. So if they go bang with the same brightness, then we can work out their distance by comparing to how bright they actually are. And we can measure the expansion rate that way between us and the galaxy. And the thing is that when you do this, the two methods now seem to disagree with each other. Although I'm going to have annoyed people, possibly 1 or 2 of them in the room, by saying they disagree. So I'll show you the actual results. So this is over time. And in black, so this is the speed with which we think the universe is expanding. So you can see it's roughly 70 kilometers per second per megaparsec. So a megaparsec is about 3 million light years. And so for every 3 million light years, every second, that gets 70 kilometers bigger. So you'll see that that's not very much, right? So that's why we don't really notice the expansion of space in our daily lives, right? It's a small account, unless you're looking on very large scales. In black are the results from the people who study the microwave background. In blue are the people who study supernovae, and there's this gap in between that's opened up in the last few years. Now, scientists are particular when they say 2 data sets don't agree with each other. So to my joy, I really like this. We've decided this isn't a disagreement and it's not an argument. This is a tension. So this is known as the Hubble tension, and it's the biggest problem in cosmology, that these 2 methods don't agree. Either we don't understand something about supernovae, or we don't understand something about the cosmic microwave background, and remember the early universe is simple, or there's something really wrong with almost everything I've told you. And we don't know which it is. What we need are more supernovae, and help is coming. We're building the Vera Rubin Observatory in Chile, which I've mentioned before, but I'm really excited now because the camera, here it is, this beast of a thing, this 3,200 megapixel camera arrived at the observatory just the other day. So this photo's about a week old. This camera is the biggest camera ever built for astronomy. And Rubin will do many things, but we're going to discover more supernovae every month than we've found in human history. So we've got more supernovae coming. We'll be able to do these measurements more accurately. And maybe the tension will go away, or maybe it will stay. We can also look at the microwave background in new ways, which we do for all sorts of reasons. This time we're doing it from the ground. This is the high Andes in Chile, the site of an observatory that's being built now called the Simons Observatory, an international collaboration involving American, Canadian, Chilean, British, and many more cosmologists. And they're going to look at the microwave background primarily to try and uncover evidence of what happened in the first few, not even milliseconds, of the universe's history. The very beginnings may have left their imprints on this oldest light of all. But what's fun about this is that the biggest problem isn't working out the physics of this or looking for the signals that they hope to find, because that stuff's simple, remember. Physics isn't hard for the reasons you think. Their big problem is that our galaxy gets in the way, that the dust in our galaxy shines brightly at these wavelengths and will interfere with these measurements. But what's great is that we're building an observatory. They can do cosmology. Other astronomers will use this data designed to discover the very early history of our universe to study our galaxy today. And so a new understanding of the dust in our galaxy, the raw materials that form planets and which will go on to form the next generation of stars and solar systems, will come from a project that's thinking about things that happened 13.8 billion years ago. I started by saying that physics isn't hard. But what I hope I've said in the 6 lectures this year is that our ingenuity in inventing new ways to discover and observe the universe is unbounded. And that as we found more ways to make careful measurements, often simple measurements very carefully, we've unveiled a rich and varied history that goes from the microwave background, just after whatever it was that the Big Bang was, all the way through to the point where we have a planet with people not just capable, but willing to come and hear about this stuff on a Wednesday evening. I want to end this year's series of lectures with a few lines from a poem by Rebecca Elson, a poet who was also somebody who researched cosmology. She studied the universe on the largest scales. And I think it captures how I want everyone to feel about our observations of the universe. She says, "We astronomers are nomads, merchants and circus folk, all the world our tent. We are industrious, we breed enthusiasms, and we honor our responsibility to awe." Thank you very much.
Chris, thank you so much. That was absolutely terrific. We do have some time for questions. We'll take a mixture from the hall, and I've got quite a lot online as well. So if we don't get through all the questions, do keep an eye out on our YouTube channel and your podcast channel of choice, because we will have, I'm sure, a follow-up on those. If you're in the hall, please wait for the microphone to arrive with you. So we've got one right at the back over there.
Hello, thank you, Chris. It was a fascinating lecture. I'm quite naive, but you said some of the simplest ideas create a huge amount of research. One thing I'm aware of is that the further into space we look further back in time, so that we get towards 13 billion years ago, we get to nearer the Big Bang. And your evidence is that because of the redshift, things are moving away, accelerating more rapidly, and things locally are not accelerating. Does that suggest that maybe we're looking at the acceleration just because of the Big Bang, near the Big Bang, rather than locally, and we're getting the wrong end of the stick?
Yeah, this is a really good question. So just to paraphrase briefly, and there was more to this, but let me answer one aspect of it, which was, we know that the expansion we seem to think the expansion is accelerating. So is it just that it was different in the past, and as we look back, we're seeing these effects? So people have thought about that. One thing you might predict, if that's right, is that we wouldn't necessarily be in the center of whatever change that was. So what people do is they look at, maybe if I just use this half of the sky do I still see evidence for acceleration exactly the same as I see this way? And as far as we can tell, there's no difference. And so it's quite hard to explain, unless there's some magical reason why we're right in the middle of this expansion. And remember that I said, just from the fact it's expanding, there's no reason that we're in a special place. So you either have to say that we're really lucky and we're in the middle and this is happening, or you need another explanation. But it's not a naive question at all. It's really important to consider these effects because we're looking at a universe that's changing as the light was traveling towards us. So thanks for getting us started. Great question.
I'll take one online and then we'll go back into the hall. So one which I was tempted to ask for myself, actually, which if the universe is expanding, are there any theories about what it is expanding into?
Oh, I hate this question. It's not that it's a bad question. I promise it's not. It's a perfectly sensible question. But I know I'm not going to say anything that's satisfying. But let me talk for 60 seconds in the hope that I might hit on something. So the reason it's not a good question is that it's perfectly reasonable, right? You're imagining, when I say the universe is expanding, you've all got in your head a thing that's probably round and has got some stars on it called the universe that's getting bigger, right? That all makes sense. You know, that's why if you call it the Big Bang, fine, it exploded and then it expanded outwards. We can all do that in our heads as well. But the question I have to ask you is where you think you're watching that from. Because if you've got this ball of stars that's getting bigger, you're viewing that from outside the universe. And so that's not, all I can say is that that's not a sensible place to put yourself, right? That doesn't exist in our physics. You've given yourself a godlike view of the thing. And so what it is it's not an expansion, it's a stretch. So it would be like, imagine if we turned this stage into a travelator that split down the middle. So you started going that way and I started going this way. We'd be getting further apart because the stage itself would be expanding. And I think I've now talked for long enough that you've forgotten that I haven't answered the question. But there is no good answer to that because it rubs up against how we visualize things. So yeah, sorry. If you're online and you know an answer, please put it in the comments and I'll credit you forevermore.
Yeah, thanks very much, Chris. You mentioned earlier that some astronomers had difficulty accepting the Big Bang Theory because it didn't seem like essentially good physics or understandable physics. And of course, Fred Hoyle and others championed as an alternative the steady state theory of the universe, which was the idea of an ever-evolving, ever-expanding universe with no beginning and no end. To what extent, with the luxury of hindsight, bearing in mind that the steady state theory is now rejected by almost all astronomers, to what extent did the steady state theory seem like better physics, if you like, than the Big Bang Theory?
Yeah, it's a good question. As you described it very succinctly. So the steady state it didn't try to deny the fact there was an expansion, but the idea was that you'd have no beginning, that the expansion there'd be constant creation of space and presumably raw materials and so on. So I think whether it's better physics at the time or not is a matter of taste, I think. It's about, do you wrap up all the stuff we don't understand and say, all right, that's the Big Bang? Or do you have a mysterious force that continually creates space that we also don't understand? So I think that really is a matter of taste. What happened pretty quickly after that, into the late 60s, just from things like counting the number of things that radio telescopes could see on the sky, was it became clear that as we looked into the distant universe, it was different from the present-day universe. So things were closer together. Stars were younger. And so once you get to that point, I think it's very difficult to explain it, because you end up with a steady state that needs to create the illusion that the distant universe is earlier, and at that point I think it falls apart. Now Hoyle wouldn't have agreed with that. He stuck to his guns all the way through into the 1980s when he was doing things like picking fights with the Natural History Museum in his spare time, and which of us hasn't done that? But I think at the time it makes sense, but there was a core group, mostly in the UK actually, the steady state was the British theory, where there was a small group that clung on, I think, past the point that the observational evidence had made it just more complicated. It's not that it's wrong, but you needed so many fudge factors that you were essentially putting little Big Bangs in all over the place, and at that point you might as well have one big one.
I can take a couple more online, one of which I think probably you can answer quite quickly, the other one might be a bit more involved. This is a sympathy question, really. Someone saying, I've asked this at every lecture in the series and sadly yet to see it asked. So on the last
Pluto is not a planet. Sorry.
On the last lecture of the series, could it be the Mysterons?
It could always be the Mr. Arms, but no one will give me funding to research that. So see also clangers and, yeah.
Another one which we have potentially one for our Professor of Divinity, but does it blow your mind as much as mine when you question why is there anything at all? I get the expanding universe, but why anything at all to begin with?
Yes, it really does. And I think one can distinguish, when we say Big Bang, I think we make things more complicated by meaning, there are two different things we mean when we say Big Bang. One is the fact that the universe was in a hot, dense state 13.8 billion years ago. And I think, as I've shown, there's lots of good observational evidence for that. There's also, when we say Big Bang, we mean the moment at time equals 0 that started everything. And we have no observational constraints on what that is, other than that the universe existed and it was in a form that it could evolve. But beyond that, it's very difficult. There's some mad theories. There are some speculative theories. If you read enough science, popular science, you find theorists who are peddling ideas like the universe causing itself, because time is on a loop, obviously. There are nice ideas, there are fun ideas about, in the far future, maybe our universe will bud off baby universes, and that causes the Big Bang. And they're fun speculations, but we haven't yet worked out how to test any of those ideas. So we know that the universe was in a hot, dense state 13.8 billion years ago, after something called the Big Bang that we don't understand at all.
Chris, there's Alan Guth, I think his name is, who one of his predictions was that there was a sudden expansion of the universe. I don't know if that was right at the beginning. But what I wondered is, if we could go back to that moment when that sudden expansion was happening, and we were making measurements, either quantum mechanical measurements or astronomical measurements, would the laws of relativity and quantum mechanics hold at that moment, during that sudden expansion?
Yeah, so the expansion, I didn't quite recognize the name, but it may be the case. Oh, Alan Guth, yes, of course. There's a group of people, including Guth, who in the 80s had this idea that you can solve lots of problems in the universe if you have what they call a period of inflation. So it's in the very early moments of the universe. This is what the people building the new Cosmic Microwave Background Telescope hope to see the effects of in the CMB. So you need something like when the volume that is our everyday universe, our observable universe today, was a pinhead, you need to instantaneously turn it into a grapefruit. Sorry, to something the size of a grapefruit. Otherwise, that's a whole different cosmology. See, there's a new idea. But that needs to happen in much less than a billionth of a second. And that explains things like why the CMB is so uniform, because any structure would be washed out, because we're now looking at a tiny fraction of it. So those are good ideas, and we're trying to test them. I think most cosmologists believe in them, but we don't have any direct evidence. There was a false alarm back in 2015 where a bunch of people studying the microwave background thought they'd found evidence for it, and it turned out it was our galaxy getting in the way. They'd mistaken the dust for the signal they were looking at. If you were there, what would you measure? Well, that's a question for somebody much more theoretical than me. It's not a problem for relativity, because space can expand as fast as it likes. Light can't travel through space faster than the speed of light, but space can speed up. So you can describe this stuff with the equations of general relativity. What on earth's happening with quantum physics at the time? It's difficult to say, except that quantum physics tells us that empty space is full of strange fluctuations. Particles appear and disappear all the time. If you suddenly inflate a universe where that's happening, you produce a set of ripples, places that are slightly more dense and slightly less dense than you'd expect. You end up with something that looks pretty much like this. And so the seeds that go on to form the galaxies may have been microscopic quantum fluctuations in the early universe. And if you understood all of that, you're better than I am. But those are the kinds of ideas that we're playing with. So yeah, thank you for adding that in. That's a great question.
Ladies and gentlemen, we have had this evening a fascinating insight into the beginning of the universe, but I'm afraid the end of time is already upon us. Please join me in thanking our speaker this evening, the 39th Professor of Astronomy at Gresham College, Professor Chris Lintott.
Great. Thank you.